next time. I want to introduce our speaker today, Mark Lupisella, who's the Exploration Integration Manager of the Exploration and Science Communication Division. And I guess Mark received his BS in physics, an MA in philosophy of science, and a PhD in evolutionary biology from the University of Maryland, where he did dissertation on modeling microbial contamination of Mars from human missions, etc. But anyway, he's going to talk to us today. He's also going to have some help from Cliff, and maybe Ron and other people will help along the ways, but we'll let Mark start there. So, thank you. Yeah, if you want to ask questions during the talk, Mark.
Yeah, I was going to say, feel free to just jump in. I admittedly, I have a lot of stuff, kind of like a lot of little things. So I was thinking I would just give an overview of what Goddard is doing with respect to Artemis, and it's kind of a lot. And even what I touch on is not going to be all of it. So I'm going to tend to focus on things that I'm more directly connected to. And so the original vision here was going to be Cliff talking Lunar Ice Cube, and then I was going to have someone talk about base camp planning, and I was a little involved in with Dan Lewis, some of you know her. And then Dave Folta was going to talk about Lunar Ice Cube flight dynamics. So not going to really have time, so I'm going to try to keep my talk to 15 minutes, so I will go fast. So if I say something that you don't understand or you want clarity on, just stop me, raise your hands, and we'll just stop in a moment. And, but I'll just ask for your patience because this is going to be kind of a whirlwind. So this is just kind of a nice little graphic bubble overview. And again, this doesn't really capture everything, but across the top, space communications and navigation, I'm sure there are tons of people here who have had some connection to that. I'm kind of curious, if you haven't had any connection to any of this, just raise your hand, because I'm kind of curious. Then space weather, heliophysics, anybody had worked in that? Yeah. Lunar planetary science, any planetary science folks? Spacecraft instrument, technology development, of course. Search and rescue, I don't know if folks know that we have done a lot in search and rescue. That's kind of a big deal. It's been at Goddard for quite a while, and not a lot of people know about it. It's a little bit more on the development side, but still it's involved in operations. This bubble here, Agile Launch and Rapid Prototype, that was meant for to capture Wallop's interests and capabilities. And then exploration architecture systems and in-space services. I tend to be a little bit more in this bubble, and part of my job as this exploration integration manager, which don't ask me to explain that too much, because it's one of those amorphous titles that can mean a lot of things at any given moment. But anyway, part of my job is to kind of integrate a bit across all of this and make sure that our Artemis customers and our Mars customers too get what they need from Goddard, because we do have quite a lot to offer.
I've got to ask real quick. I can't.
Yeah, please.
Search and rescue. How high on the moon?
How and why on the moon?
Are they planning on getting lost before they even get there?
So, and of course, this search and rescue is for terrestrial applications.
Yes, I know.
But on the moon, we're envisioning that would very much be
down the road
something good to have.
Yeah, I'm not saying it's not.
Just in case. Just in case it happens, right? So, you know. Actually, it's funny you raise that, because a lot of people do laugh a little bit at this idea, because in the early part of it, but the rescue part of it, you know, imagine that there's got to be rescues, you know precisely where they are, you know, how long they've been there, make sure all the comms in place, all the PNT, position navigation, times and stuff is in place. So, yeah, in fact, that was one of the things I've been poking on a little bit, because it's one of these problems where it's a longer term thing, but why not get ahead of it? Why not get smart about it now? Why not build it into your infrastructure now if you can? Get all the programmatic stuff lined up if you can. So I don't work directly in that, but we've got really smart people and good managers that are really doing a lot of advocating and getting that done. Well, I thought I would do this real quick, and I do have to watch the time here. So we're ending, the whole thing ends at 1, is that right? Or sooner? Around 1? Okay. So this is the new organization, and everyone always likes looking at org charts, right? I have to spend an unusual amount of time analyzing org charts, because they constantly keep changing too. But this is kind of interesting because we've gone back to the split between exploration systems development, which is why this is now called development mission director. It used to just be called exploration systems mission director, and then there was space ops, basically, which was SOMD, space operations mission director with station. Then we went and merged those two. Then they got separated again very recently. So this is the new exploration systems development mission director. So most of what I do is connected here, and most of what Goddard does, actually I shouldn't say, probably most of the funding that Goddard has with Artemis is probably coming out of this directorate. So I'm putting in red circles things that Goddard is fairly directly connected to. In this case, actually very directly connected to, because Ruth Ann Lewis leads this effort, multi-center effort. And this is very fun and interesting stuff. I mean, she's literally working on what is a base camp, lunar base camp, going to look like. What are some of the operational, and hopefully I'll be able to go into a couple of slides on that. Then there's this technical integration office underneath. And it's sort of implied by the way this is set up that this architecture, this is actually a strategy and architecture office. And then there's this technical integration office, and there's a bit of a handoff that needs to happen there. And the technical integration office is what it sounds like. It takes the architecture vision, it starts to integrate more tightly, and then starts to inform the rest of these programs underneath. So here's, okay, well I should point out, this is Artemis Campaign Division here. So that's where the Gateway program is. And then human landings, I assume folks know what the Gateway, they might not know what the Gateway is. Sort of like a mini space station, although we don't want to talk about it that way. It's kind of a mini space station around the moon. Yep. So then human landing system is under this as well. I'll touch on a little bit about what we do there. And then there's a new program. It's actually, the acronym is EHP, EVA and Human Mobility Program. So it's a problematic acronym in some sense, but they're merging this now, and we're doing a number of things in this area as well. So we really, when I say we too here, I don't necessarily mean all of Goddard. I mean, Goddard is involved in Common Exploration Systems Development Division with Orion, Space Launch Systems, and ground system, at least in a couple of ways, like COM, for example. COM touches everything, so Goddard is involved there. I'm not circling that because I'm not going to focus on that per se. And then in Mars Campaign Development Division, the reason I want to put this org chart up is because this is kind of exciting. I mean, this is, to my knowledge, unless somebody here knows differently, the first time that the exploration, human exploration side of the agency has specifically stood up a division devoted to Mars. So this division is supposed to pull together the campaign and really integrate, get all the technical development stuff going, get all those programs going. And a piece of it right now, we just had a review at Ames recently, is exploration capabilities. This used to be called Advanced Exploration Systems, which was around for about 10 years. Advanced Exploration Systems spun off Gateway, because it incubated that for a while. It spun off Human Landing System, it incubated that for a while. And then the rest of it moved into the Mars Campaign Development Division, and there are a lot of small-ish, highly diverse projects that go on in exploration capabilities. This is where our Lunar Ice Cube mission was, which Cliff will talk more about the instrument. And that was what went up recently on Artemis, and we'll talk more about that as the talk unfolds. And then another thing we have here, this isn't everything, but another thing we have that's kind of interesting is this multi-function nanosensor platform. So there's a person at Goddard named is Mahmouda Sultana. I don't know if anybody you know her or not, but she moved from the 500 side recently to the 600 side, and she's doing great work on essentially miniaturized sensing platforms. Very low SWAT, low power, low weight, and really fairly generic and extremely, extremely sensitive. Right? Parts per billion detection capabilities are pretty much any interesting molecular species we think we're going to be able to get with this. So I'm particularly interested in this because I'm a little bit interested in contamination. And one of the things we want to do on the moon is set up a really decent environmental monitoring network of some kind. The kind of instrument that she's working on would be a good fit for that kind of network. Okay, so I kind of mentioned all these at a high level on the org chart. So for the architecture, if I get a chance, I've got some slides in here, and I'll touch on some of that. I really would like to. It's pretty interesting. Under technical integration, you saw that box up there. We're actually getting quite a lot of science support. So Goddard is essentially seen as a science agency. So people come to us, people in exploration, come to us a lot to get science consulting, science input, science planning, ConOps, etc. Of course, we have LRO. Is there anybody that worked on LRO? There must be a couple of people here who worked on LRO. Oh, yes, maybe, yeah. So technical integration, working at fairly high level with planetary protection. I'm in the middle of making some contributions to a paper for planetary protection. So science, though, is the big story there for technical integration. The human landing system, this is a different kind of program. This is a commercial program, meaning that effectively NASA puts together a lot of requirements. We put out what is a contract, a request for proposal, and a contract comes from that. And so many of you probably know that SpaceX is the company right now under this program, but there's a new RFP underway, and so there will be bids to that, and there will hopefully be another provider that will come on board to be another commercial entity. That was the original plan, was to have at least two, partly so that there could be some competition and maybe some backup. And that didn't happen because for a variety of reasons, funding maybe wasn't available, et cetera. But now we think we're going to be able to get another provider on board. So what is our job at Goddard? What is our job as an agency? Well, a big job is insight. So insight is providing a program with a lot of detailed insight into what these providers are actually doing. So we at Goddard, we lead the software insight for HLS right now out of Code 581. We've had various people over the years from Code 580, the software division, contribute to that, including Dave McComas is back there and Elaine Shell. They're previous both branch heads, right, of flight software branch. And so I'm constantly pulling out the flight software branch to help out. So they've played a big role in that. You'll hear more about that with Gateway. Actually, I could probably just jump to Gateway right now. I'll come back to human landing system stuff if we have time. There's a couple more interesting things that we're doing there. There's two different flavors of support for HLS, I should point out. One is insight, which is quite different than collaboration and GTAs. Collaboration and GTAs is actually working with the provider to actually produce something, whereas insight is more what it sounds like. It's an insight. It's kind of an oversight function, but not really, strictly speaking, it's not an oversight function. It is an insight function, if that makes sense. So for Gateway, our big contribution right now is core flight software. So there's been a development effort underway for years with core flight software. I think Dave's talking about it next month, right?
Yeah,
next month. Yeah. And then MBSE, model-based system engineering. We're not doing that right at the moment, but we were doing it for a little bit of time. And I think we're probably going to be coming back to that. Model-based system engineering is kind of interesting because it's sort of newish, even though maybe now it might not be considered new by a lot of people, but maybe say in the past 10 years from NASA, it's gained a lot of momentum. And so finally, we've got a lot of big programs taking MBSE seriously. We've got a couple of real experts coming out of 580, the software division, and some of them actually leading efforts for the whole agency on MBSE. One of those guys, Rob Morgenstern, had help on HLS and Gateway and other things. Then there's a Lunar Terrain vehicle. This is kind of new. This is under that EHP box I showed you in the slide prior, the EVA habitation program. So Lunar Terrain vehicle is part of the mobility program in that organizational box. And underneath that, this is what HLS did. They're trying to put together lots of government task agreements. So that's what they sound like. Formal agreements, we're signing off on costs. Here's what we think we're going to be able to do for you, the provider, who's basically taking the lead. But we're going to help you get the job done. We're going to help you build a lunar terrain vehicle. So we're just having some conversations right now with some interested parties, and we can't talk about those details at a later date. We'll be able to get into more of those details, but in terms of who we're helping. But right now, nothing is formalized. It's just conversations, but there's some interesting conversations. How do we survive the lunar night? Can you provide us with autonomous guidance, navigation, and control? That kind of thing. So then some other things, Lunar Ice Cube, I'll skip that for now, and then we'll come back to that. Although I guess I shouldn't skip it, because it launched on Artemis 1. It was one of 10 CubeSats, and we have not been able to make contact with it, which many of you may know. So it's 6, I believe 6 of the CubeSats, 6 of the 10, we have not been able to make contact with it. It was actually 8. Is it 8 now? Yeah. Effectively lost at this point. So we're still looking for CubeSat. We work with the university who led this, Morehead State University. We built the instrument. We Goddard. Cliff's going to talk about that. Cliff led the development of that instrument. We also led the flight dynamics with Dave Folta and Son Diaz. I don't know if any of you know. Some of you must know Dave. Maybe some of you know Son. Oh, and this young guy right here helped a little bit. Alex Mason. Yeah, I've already mentioned that we have a youngster in our midst. Invited at the last minute to join him. He's interned at Goddard 2 summers. Worked with Dave on flight dynamics. We also did attitude control stuff. So anyway, actually tonight, one reason why I can't stick around too much is I'm flying to Marshall tomorrow because we're having a powwow between SLS and the secondary payloads, these CubeSats that flew and that have effectively been lost. And one of the theories is there was a lot of tumbling as these were released. And the tumbling was difficult to recover from for a lot of these smaller spacecraft that maybe didn't have big enough momentum wheels, et cetera. There's a whole interesting set of conversations that people had about this. We kind of anticipated that this could be the case. They even put larger wheels in the vehicle to help with detumbling. But anyway, unfortunately, it is speculation at this point. We don't know because we don't have any data for the spacecraft. We know that one other spacecraft, BioSentinel, another CubeSat, had a very high tumbling rate. And it was able to recover. It was the first out. So one little possibility is maybe as you pop more of these things out of the ring, the dynamics of the ring gets affected by the number that you've already shot out, right? You had a little bit of dynamic. You're supposed to be spinning this ring 5 degrees a second, I think. So anyway, hope to learn a lot about that in the next couple of days at Marshall. Lunar Flashlight, we have the project scientist, Barbara Cohen, and that's a very interesting mission. Was supposed to fly on Artemis 1, didn't make schedule, got a backup flight on SpaceX, had time to learn from the kind of challenges we were having on Artemis 1 with the CubeSats that got shot out at high rotation rates. So they actually got to prepare for this in a way that maybe others did not. So there was a certain ironic benefit that they got from not getting put out to Artemis 1. Unfortunately, 3 of these thrusters essentially failed, and the 4th is failing. They are trying to figure out how to get a flyby out of it now. So fingers crossed. And then that flyby may lead to subsequent flybys of the moon. So there may still be a chance for a science mission. So fingers crossed on that. That's led by JPL and Georgia Tech. Mars Environmental Dynamic Analyzer. We have a scientist who's a lead scientist on that instrument. And then I mentioned the multi-function nanosensor platform. We're also starting to support JSC and radiation-hardened displays. So, displays on computers, displays on head-mounted displays. We've got to make sure these things are going to function in high radiation environment. Seems like it's probably a non-issue, and it may turn out to be. In fact, some of our initial indications are that maybe off-the-shelf products are going to be okay but we still haven't done the thorough testing we want to do. And that's what we think we can help JSC with, is actually doing the thorough testing in facilities that either we have or that we work with outside of Goddard. And then I'll mention additive manufacturing, or it's not exactly the same thing as 3D printing, but it's effectively the same thing. I was just in a little workshop this morning, actually, where we had 30 sort of mid-career folks in there learning about additive manufacturing, how to use it, and then more importantly, ultimately, how to validate it, how to verify it, how to stick to certain kinds of standards, maybe contribute to the development of new standards. Interesting little workshop that we were having at Goddard, and that was Andrew Clendening that led the organization of that, and he comes from the SMA side of things, safety and mission assurance, and is actually focused on safety and mission assurance with respect to 3D printed parts, which makes sense, right? Because these parts can have plenty of issues. So this is how we're going to make stuff. If this is how we're going to make stuff on the moon, we would really like to make sure that we do it properly, that these things function properly, meet all the safety requirements. Okay, I think I'm going to essentially wrap up and just show you a good little title here, an anarchic example of why site planning is important. Don't destroy what you may desire to explore in the future. And so anyway, Ruth Ann Lewis is working hard on that, and we got a whole big team, and Antarctica is, did you say working in Antarctica? Yeah. So we'll have to chat a little bit more about that. As a matter of fact, it's a great environment to learn about planetary protection and protocols for making sure that we don't destroy life that might be there. I will not go through all this process, site analysis, design, planning objectives. These are just things that Ruth Ann and team are contemplating to try to essentially optimize. It's a strong word, but to try to optimize what base might look like and how it might operate. Figures of merit, super important. Spent a lot of time talking about what these figures of merit should be. There's just sort of two different flavors here in this slide. This is kind of a recent development. Placement farms and then design and management. You can imagine, I'll just point out Mars forward applicability is on the list, right? So many of us think that would be a really serious farm, and it ought to be weighted heavily. But as you can imagine, there are lots of legitimate differences of opinion about how Mars forward our lunar activities should be. But since this is probably our only real testing ground before we go to Mars, one could make the argument that we really ought to do as much as we possibly can on the moon with respect to Mars forward. But not everyone shares that point of view, and it's understandable because there's lots of near-term, high-priority, difficult things to do, especially if we're going to stay. I'll skip this. It's basically an example of a chart that Ruth Ann's using to kind of show how various assets relate to each other. There's some tentative conclusions there. This is just a slide we've shown with some science that relates to human exploration. The LRO on there, Lunar Ice Cube. And there's a bunch of other things that fit into supporting human exploration. All right, and these are just more details that I was going to have this back up anyway. So I'll stop there, and well, first of all, before I hand it off, you can have a quick discussion or any questions or anything anybody wants to bring up, and then I'll hand it over to Cliff. All right, so I'm going to set up Cliff and say Cliff has been our lead engineer on the Ice Cube instrument. He's been invaluable. Unfortunately, he relied on spacecraft, but learned.
Unfortunately, retired.
Yeah, recently retired. But we learned a lot. And by the way, that was part of the process of these CubeSats too. It's one of the reasons why some of them are university-led, like Ice Cube was university-led. And having universities participate heavily, like Flashlight, they're operating that mission out of Georgia Tech. So and I think we as engineers and managers learned a lot from the whole thing, working with Moorhead State, which was great. Learned how to miniaturize an instrument that might seemed like, oh, you should be able to do this cheaply and quickly, and the details, of course, Cliff knows the details better than anyone. So I think we learned a lot. I think we're going to be able to apply a lot of those lessons going forward. And I think we learned a lot from the instrument development work in thermal in particular. I also mentioned real quick that on flight dynamics, it was not trivial either. So Dave Bolton and his team had to do a lot of work. Every time there was a slip in the schedule for Artemis launching, everything had to get reworked. And it wasn't necessarily trivial. It was a low thrust engine going to the moon, doing a Sun Earth L2 dance for some part of the orbit in any of the trajectories. So Dave was going to talk more about that, and he can come back and talk more in the future. But we learned a ton just from going through that process as well. So here,
thank you, Mark. So let's get my slides going. I introduced myself earlier. I worked with Mark for at least 6 years, I think, on Lunar Ice Cube. It started up in 2016, I think. Was that when or 2015?
Yes.
So it was the next step proposal. It's called from headquarters. They put out an announcement of opportunity, and Moorhead University in Kentucky won the right to make the spacecraft. And then we at Goddard got to build the instrument. So as Mark mentioned, I wore a bunch of different hats on this instrument development. I was the instrument systems engineer, I was the electrical system engineer, I was the lead. I was QA, believe it or not, because it's a very high risk, low formality development effort, because it's considered a do no harm classification, where James Webb is class A, the best of everything, redundancy, full blown. This one is on the opposite side, a lot of risk, low cost, relatively speaking. So anyway, let's see what we got. Here we go. Okay, so this is Lunar Ice Cube, the spacecraft. And as a scale, this piece right here, the spacecraft itself, is about the size of this black box. That's how big that is, literally. And that's called a 6U spacecraft. That's about as small as it gets. I mean, there's nanosats that are smaller, but these is pretty small. So Lunar Ice Cube was developed, like I said, at Moorhead. And in Kentucky, they did the whole spacecraft. These are the solar arrays. And you can see all the constituent components that go into this. This little spacecraft has everything a big spacecraft has. It's got to communicate. It has to be powered. It has solar arrays. It has attitude control stuff. It has a computer inside of it, the CNDH, a command and data handling system. So every headache you get with a big spacecraft is loud and proud, and even worse in a little tiny spacecraft. So anyway, can we go to the next slide? So just to give a brief overview of Artemis, which is this very impressive rocket that went up in November of 2022, and it was a success. The Orion capsule at the very top went to the moon and came back and splashed down successfully in early December. So the primary mission of Artemis was a wonderful success, which is great. Up in this area here, that's Orion, the capsule. This is the equivalent of what we did on Apollo back in the 60s, where the astronauts sit in here. This capsule returns ballistically to Earth. It's very similar, a lot of parallels there. But anyway, once this is gone, this part here, right in here, are where this ring is, and each one of these is a little CubeSat. There were 10 of them. One of these is Lunar Ice Cube. I forget which one it is. When they deploy, they're literally spring-loaded deployers. Command goes, releases the mechanism, and this thing just spits out. Right? And as Mark mentioned, this is all spinning at about 6 RPM while they get deployed at different times. So we're up here, and as a friend of mine said, we were kind of like barnacles on a whale, because the big important thing was Artemis, and we were the secondary payloads. So anyway, we got up. We may have deployed. We think we did. Unfortunately, there was a high failure rate with the CubeSat, which Mark is going to be going to Marshall tomorrow to talk about some of the theories why that might have happened. So anyway, we keep going. So in Building 8, which many of you I'm sure know where it is at Goddard, next time you're at Goddard in the next couple of weeks, I'm probably going to move this to the museum over in the visitor center. But right now this is set up, this is a full-scale model of the actual Lunar Ice Cube spacecraft, and with the solar arrays, and as soon as you walk in the building, you go on the left, and there it is. So it's pretty cool. Moorhead made this. They had a retired engineer that was modeling, and he put together this beautiful 3D printed model and sent it to me, and I put this display up 2 months ago. So here's a little more detailed look at Lunar Ice Cube. So as I mentioned, there's X-band antennas, there's a command and data handling computer, there's, I won't go through every one of these things, but the solar arrays. This right up here is the Birch's instrument, and the Birch's is a broadband infrared compact high-resolution infrared spectrometer, basically. So that is about the size of a Kleenex box, the big one, not the little one, but the one that's about that big. That's about the size of it. It weighed about just shy of 4 kilograms. This whole spacecraft weighed 14 kilograms. So we had the big mass challenges. We take up maybe, I don't know, 1/5 of the volume inside the spacecraft. This is a close-up of the instrument itself, a computer-aided design model. So I'll just give you a brief tour of it. So what makes an infrared spectrometer work is the actual detector itself. This is a detector. It's an infrared detector made by the Teledyne Corporation out in California, and it has a million pixels. If you're familiar with your cell phone cameras, today a million pixels is laughable in the picture industry. You get 30 megapixel cameras all over the place, but for flying things in space, the density of these detectors has been evolving for some time. This detector is one of the spares from the OSIRIS-REx OVIRS mission. OSIRIS-REx went up to take a piece of Bennu, which is an asteroid that we know about. It landed, it took a piece, and it's sending it back. I worked on an instrument, one of 4 instruments that had this exact detector in it. Not that one, but the best of the best flew on that one. This was one of the rejects, believe it or not, but it still worked pretty good. So we got it for free. It's about a $2 million detector for nothing. So thanks to the folks on OVIRS that gave it to us. So anyway, so we have a detector in there. Our whole idea is to look at infrared light, and we are interested in infrared light in a wavelength range of about 1 to 4 microns. Okay, so in there's this ability to basically look at energy in that wavelength range and basically correlate it to the periodic table, the one we all learned about in chemistry. So this basically the ABCs of an infrared spectrometer. So anyway, this has to be cold, and preferably down around 120 Kelvin, which is absolute zero is 0 Kelvin. So that's pretty darn cold, right? So to do that, we have a cryocooler. This is a little refrigerator, basically, and there's a little piston in there that goes up and down, and it moves a little piston up and down in here, and in a very similar way that with the way air conditioning your car works, your refrigerator, this does this very similar thing. So it makes this very cold, and we have a little strap, and we can back the detector. When this thing's running, it would bring the temperature down to around 120 Kelvin. So that was good. And this is called the optical box. It has a special low emissivity coating inside that we didn't want a lot of reflections inside. There's 2 mirrors. There's a primary mirror here and a secondary mirror. Light enters here, gets bounced off of here, goes to here, and comes in here. So that's our path. This faces the moon. Would have faced the moon if we had made it. This is the electronics that basically drives the whole thing, and is the smarts of the instrument. Provides power, provides commands, takes the data, puts it into packets, and sends it down to the ground. This is a really cool thing we worked on called the adjustable field stop. This is a variable aperture mechanical device, electromechanical device that maintains our visual perspective of what we're seeing on the ground as we're changing our altitude. It's like looking through the peephole in a hotel room, and there's somebody on the other side, and you're moving back and forth. You can see more or less what's on the other side of the door. You You can also effectively do the same thing by changing the size of the aperture. So that's what that does. It's pretty neat. Anyway, let me go on here. And by the way, if you have any questions, just feel free to ask. This is just another perspective to show you a different angle. Again, we have the detector here. This is, we call this the snorkel. It's basically like the sun filter you put on the end of the sunshade you put on the end of your old camera to keep instant light from coming in. Yes, Alex?
Why did you have the light bounce off the mirrors instead of just going straight?
Oh, okay, so that's a good question. So the light, the question is why did we have mirrors instead of just have the light come straight in? And the reason is we have to actually, these have prescriptions to them. They're designed to actually present the light to the detector in a very specific size, and also it's collimated. The light is actually separated out into different wavelengths, and as it approaches its target. So the optics were very important. The other thing is that we're 100 kilometers to 1,000 kilometers above the surface of the moon. When we come around, we're at 1,000 kilometers. When we end up in our midpoint, we're at 100 kilometers and then back to 1,000. So the optics had to be designed to look at something that far away. So that's really, there's multiple functions. Good question. Let's see, what else here? This is, this is funny. After about 3 years of working on this, we realized that if this ever accidentally looked at the sun, the detector would be fried in like 300 milliseconds. Gone. So, and not only that, if the blades of this little adjustable field stop here were closed and the sun hit this, the energy would melt that, burn a hole right through it. So we said, well, that's not good, right? We need to fix that. So we devised this this door. It's basically a garage door that we have a little stepper motor here, and there's a little rack and pinion gear like your car has, and we could open and close this and open and close this at will with the trans. And that protected us. So when we launched, we were going to have this closed, keep ourselves safe, because there is always a possibility that, whoops, we lost control and we're looking at the sun, and we didn't want that to happen. So anyway, so that was interesting and really fun to work on, actually. So these are just some really internal images. We had to develop a really low thermal conductivity harness that goes from this box, which is about 300 Kelvin or room temperature, to the inner sanctum of the detector, which is here at about, this is 300 Kelvin, this is about 120 Kelvin, and it's only like 6 inches away. So we had to make this really interesting custom cable that was very low when it worked. And that took a bit of effort. Everything about this was new and had to be made, which was really fun. I loved working on this program. Even though it failed, I really learned a lot. I learned from great people, great experience, broadened my horizons as an engineer. I got to see the full gamut of what a spacecraft has to do in something that size. It was really cool. Anyway, so just I don't have a lot of time to go through this, so I'll just say, there was a lot of really incredible work that we did to make sure that everything was there to make us, be able to look at the light that we wanted to look at. Here's just a quick overview of our orbit. It would have been a 7-hour orbit around the moon. We loop around the moon every 7 hours. And when we came in, we turn on the instrument, we start making observation, and you notice this distance is greater than this distance. This was the 1,000 kilometers I talked about. This is the 100 kilometers, and this is the 1,000. So we come in, and this would take about 40 minutes. We turn on, we start taking pictures, basically, and digitize the data and send it down to the ground. And we would have been able to, look at our science that way. This is probably redundant from what I just talked about. Go down here. So this is what I was talking. This is really the essence of what the instrument does. This is the detector surface. It's 1,024 pixels by 1,024 pixels, which multiplied out is a little over 1 million pixels. We had these what they call linear variable filters. They're little prisms, and they're suspended in a frame a short distance above the surface of the detector. LDF 2, 3, and 4. This is exactly how OBIRS did it on OSIRIS-REx. We copied their design. We actually got leftover LDFs from them. The LDFs for OBIRS cost about $800,000. We got them all for free. So again, huge savings thanks to OBIRS. So bottom line is it takes, it's hard to see it, but it takes the wavelengths of light coming from the moon, the reflected energy from the moon, and carves it up into different ranges. This is like 1 to 1.8, this is 1.8 to 2.8, 2.8 to 4.2. So these are the wavelengths of light, just like a prism does when you see a prism. If you play with them as a younger person, like I did. So bottom line is, here's the periodic table, right? Here's all the different things that we can see. So all these components like water vapor, liquid water, hydroxyl, bound water, absorbed water, ice, and other ion oxides, all these different materials. So this is our holy grail science. This is what we want. The most important thing to us is what happens around 3 microns. And why we wanted to look at that is what happens to water on the moon as a function of time and position around the sun. We want to know if water is absorbed into the soil or released as a function of where we are in our orbit. So this was supposed to be a 6-month mission, and for half a year we were going to start. And of course, you know, for half a year we're going around the sun, so there's a lot of different thermal and let's just call it moon weather scenarios going on during that 6 months. So this is really interesting. This is really exactly why we did this, to see how what was showing up and what was happening to water. And why? Because water is so important for going to the moon, not only to drink, but to we can use it to make fuel. There's energy applications. There's so many things that water gives us. So these are actual images that were taken from the spacecraft and the instrument during thermal vac, where we put the whole thing in a vacuum chamber. And then if anyone knows Building 4 in Goddard, there's a big thermal environment there where we were able to put this in a chamber. And for 4 months, right after the pandemic started, hell fun, we spent 4 months suited up with masks on, putting this thing through the testing in the thermal vac chamber there. And these are the results. What shows up is a little vertical bar. Where you see a little vertical bar, there's energy that's being detected. So we were able to present energy to the detector, to this instrument, through some ground support equipment we made that shone through a special port on the chamber. And then we were able to do cause and effect, basically, and see that light from, you know, in this band at 1.985 microns, it shows up, and that equates to that chemical on the other slide I showed you. So this proved that it worked. You know, the instrument actually worked. This is one of the cards we developed that sits inside of that rectangular box called the detector readout electronics box. This is basically the smarts of the instrument, the electronics that make it happen. This is the analog processing unit, and we have a FPGA, a field programmable gate array there, which has a program written into it that basically is the smarts of the box. This is our analog to digital converter that digitized the data, and this is our power card. So this took the 28 volts from the spacecraft and produced the voltages we need for the instrument to work. This is all very tiny. That's, I don't know, the size of my cell phone, really tiny stuff. This is the 2 of them sitting on top of each other, stuck inside the chassis. Those are the connectors that help us, you know, go out to the outside of the instrument and to the detector and parts of the spacecraft. This little box is called the miniature low-cost cryocolor electronics. As you can see, it's only 3.5 inches square. This little box is what drove the cryocolor. This is what gives it its big sinusoid to make that piston move up and down to make the refrigeration cycle work. So that was important. This is actually the inside of it. And a company in California, Iris is what it's called. They made this. And a funny story, in the very beginning of this program, we got somebody in the Air Force, I think he was in Arizona, they worked on a program that had worked with this box and that cryocolor we have, and their funding stopped. And they just had this stuff laying around. And somehow we found out they had these items, and they just gave it to them. They were, hey, you want them? Here you go. So they just gave us engineering models of this box, engineering models of the cryocolor. Huge step forward. So we were lucky to get a free detector, free LBS, this original, you know, prototype hardware for nothing. You know, and thanks to the Air Force, they sent it to us. So it was, wow, this is so cool. Believe it or not, that's my last slide. I just want to say, again, since I know it didn't work, I wish it did, but I learned a lot on this program. Probably learned more on this program than I did on any other program I ever worked. I worked a lot of programs. So great people, great team, almost a skunk works type environment where because it's such a Class D, do no harm, you can do things. I made the decisions. Mark and I make decisions. I didn't have to run up the flagpole and have a huge committee type decision. It was, no, we're doing it, let's go. You know, and it was great. I really loved it. It let us get a lot done in a short amount of time. So the only other thing I'll say is, you know, this mission, soup to nuts, with the operation costs and everything was, I think, around 30 million, 25, 30 million. I worked on SMAP. Somebody over here worked on SMAP before, and I worked on the radiometer. SMAP, with all the costs put together, launch vehicle and everything, was about $1 billion. So 30 million versus $1 billion. Right now, $1 billion is the whole spacecraft. So the SMAP radiometer was probably on the order of $150 million at Goddard. So you can compare apples to apples there. $150 million radiometer, different convention, of course, and this little CubeSat, which cost Goddard probably cost, I don't know, $5, $6 million, something like that. Okay. Anybody have any questions? Yes, sir.
You were talking about a 6-month lifetime.
Yes.
But you know, we often hear about the Mars mission that been going on forever. How long do you think might actually? What would be the factor that would keep it from going? And is there a fixed thing where you know something's going to stop?
Our biggest threat against a longer mission was fuel. The ion propulsion system that we had on this, was it xenon? What was the source of fuel? I don't know. Xenon, yeah. Please.
Want to comment on this?
So,
I made Alex come because he actually kind of worked a little bit on that exact question.
yeah, so.
You want the mic?
Yeah.
So the dynamics between the moon, the gravitational pull of the moon and the sun, kind of torque the orbit over time. And so after, I think initially it was like 3 months, the periapsis was actually going to go below the surface and it was going to crash. So I was brought on to figure out a way to use the low thrust propulsion to maintain the orbit and extend it. And what I found is that we could extend it indefinitely as long as we had fuel. So Dave Folta developed this kind of spaghetti low thrust trajectory to get us into orbit, and then we happen to have a little bit of fuel left over. And so with the station keeping in place, we could extend it at least to 6 months and possibly even longer than that.
I've got a follow-up question real quick.
Oh, sure.
That Cliff maybe answered. Since you had so much fun, why did you retire? Why did you retire?
He didn't. He thinks he retired.
Yeah. They just gave me the blue badge. I really don't know what's going on. They keep coming back in a couple of weeks. I don't know. I mean, everyone has their reasons to retire. I just, life is finite. I wanted to have an opportunity, God willing, to enjoy what I could in my 60s and hopefully in my 70s. My wife retired a year and a half earlier before me. My son's out of college. He's actually working at Goddard right now in Code 545 in the Ridge. So it's, son's out of college, no more big bills to pay, working 30 years, closer to 40-something if you include, the first job you ever had, gas or whatever. 2/3 of my life I've been working. I figured now it's time to chill. And I'm lucky, like all of us, working at Goddard, working in the government, getting a pension, which is so rare. All the different revenue streams were there. It looks like it's going to work. But so far so good. So I just, it was a good time. And I had colleagues that were retiring too. Yes, sir. And I know it's a question over there. Yes, sir.
How do students at the university make the news?
So actually, I'm glad you brought that up because Moorhead University has a fantastic aerospace program. They immersed students into this in a huge way. I met dozens of students, and Alex can attest to this too as a student at the time as well. They really do bring their folks in there. They were disappointed, of course. I didn't have a lot of first-hand conversations with a lot of people I met. I mainly was talking to a lot of the managers and the assistant engineers folks. But, you know, they all were kind of pragmatic about it. They realized, you know, we tried our best. Some things are out of our control. It's high risk. You know, I think that's the other thing. And, you know, nobody died, right? I mean, my whole career I worked on some amazing stuff, and I was stressed out enough not just working on metal, you know, and electronics. And if I had to, if somebody, I don't know what I would do. It would be brutal if someone. So I think that's a perspective that they share. It's a learning experience. It's high risk. We did the best we could, and like Mark said, we learned a lot. So if we get to do this again, I think we'll, you know, we'll do things a little differently. So, yes.
So, as you mentioned, you've been working with Moorhead, and I don't think, or at least I don't remember them having a lot of experience in this area. Did you find that you had to spend a little more time helping to educate them and helping them get through the process and figure out what they were doing, as compared to working with another university that would have had much more experience?
So it's a good question as well. So my experience with Moorhead was, at least starting in 2016, that they actually had a fair amount of experience. And they brought in a couple of people from industry, like this guy Nathaniel Fike, who worked for Tyco, the deployer folks. And Nate was just brilliant, I have to admit. And he's a tireless workaholic. He will work 20 hours straight, take a 4-hour nap, come back and do it again and again and again. So this guy was like Mr. Lunar Ice Cube. So he was great. But I do think that the NASA process, the system engineering process that we know and for the most part really admire, I noticed that when you get outside of NASA, that process is not exactly the same. The rigor is not as much. So I found myself kind of micromanaging a bit, trying to offer NASA's experience, and in many ways they accepted it, which was great. Like the navigation and ACS stuff, we were so involved, it was great. In other ways, not quite as much. And I think that's one of the lessons learned would be, you know, not that we're perfect, but, you know, but it could have been a little, there were a few times when I felt like it was, you know, thanks, we'll handle it, you know. And I think in a few instances, the end result would have been better if they had let us like crack the door open and help a little bit. Right, Mark, do you think that's a fair thing to say? I mean, they were experienced. I mean, they put up other missions before.
Yeah, it's like anything else. It depends on the details of the specific technical issue and process issue. It varies. And lots of different reasons. So I was always with the mindset that we had to embrace the experiment of doing things a little bit differently. If there were a couple of corners to be done here, there was a PI, and it was ultimately his decision. Very good as a guy in terms of taking a lot of information, very good for ultimate decision making.
Yeah.
But at the end of the day, the program has its own set of constraints and finding it's a different kind of program. So
Class D?
yeah. Actually,
It's really do no harm.
yeah, not even.
Not even D.
Yeah, they're back and forth.
Yeah, and that's what made this all very interesting. So one of the big lessons might be, what's the cost you want to put into a whole bunch of little missions that might fly on one big rock? Total cost, $300 million, which add it all up. What's the cost you want to incur at what risk level spread across all these missions that might have different risk postures, but all roughly the same level, they're at high risk. What's the amount of money you're willing to potentially lose if you don't have that extra figure, or you don't have all the checks.
Without capabilities, there's no
Exactly.
what failure would not.
Yeah. So, you know, the pendulum may have to swing back as a result of this. But what we don't know is what really caused this to begin. So if it's a tip-off is,
Yeah.
then it's not necessarily the problem in the process of that there's a development per se. It might be a little bit hard to deploy itself in a vehicle and not quite having that well understood. Because QChats did ask questions about that. We had a DCS back, Paul Mason,
the deployment method is very similar to what's done in the past. Nothing new there.
Well, except that you got 10 of them.
10 of us, yeah.
Big ring going at different times.
And we're spinning a variety of distances, I guess.
So, unfortunately, this is the big question is this, because this is what I want to know at the end of the day. Are we going to be able to learn enough from this to know if we fail the experiment,
Right.
things very differently, or do we just have a deployment problem? And I'm afraid we're not going to put the answer.
That's one of the lessons learned. We get more feedback in the future.
Exactly, that's the intuition of the problem. We have some data on the total race being usually ties, for example. But that's jumping to a conclusion. We really don't know what it is.
So I think our time is elapsed. The black clock still is 20 after 1, so I guess we should wrap it up. I just want to say it's an honor to be here. Thank you very much.
Yes, thank you for the invitation.
Let's give our also, I forgot to mention earlier, don't forget our speakers next month, 2 of which are here, Lane Shell and Dave Combs, and we'll talk about core flight system software system that Goddard put together. And then in April, the Deputy Director of Engineering Technology Director, Bill Kittle, will be here to talk about the future of Goddard engineering. So join us in the next month for Dave, Lane, probably in April. We'll figure that out. Thanks for coming.